folks, so welcome back. I'm going to talk to you about two fairly pressing problems, I think is the best way to catch or describe it, that we're going to have to address. So, first one is, apparently I'm repeating myself. You remember domain sampling theory. It's important. If you would like the refresher, feel free to read the slides or go back to the previous video. Okay, but just for those of us who are zipping around, so we tend to want to create a single score, and the big question becomes, how do we do that? Well, surprise, surprise, what we tend to do is create a composite. And that consists of just adding up all the individual scores to create a total score. Now, you can see in the notation here, it says item 1 plus item 2 plus item 3 ... item k. Well, that notation indicates that we have items 1 through k. And k is whatever number we want it to be. It's a way to generalize this equation beyond just our my own limitations in typing. So when we calculate a total score for any individual, often this is just the sum of the items, which is essentially treating all the items as equally important. What's happening is it's weighing them by 1. Okay, sorry, Archie is invading the camera, which I don't know how that's going to work with fish. So enjoy, because, yeah. Alright, so I've already kind of illustrated this piece here, but that composite is making a very strong assumption that every item is equally important. Is there a reason to believe that every item is equally important? And equally good as it relates to the intended concept? No, there's not a really good reason, but to illustrate, I've included a slide here of how to think about this conceptualization. What's happening here is we've got a basic path diagram where circles indicate the construct and each little box is an individual test question. And what this is indicating is that the latent measure of depression is the product of equally weighting these items. The one there is the factor loading. And we'll talk about this in a little bit, but this is essentially the diagram that creates a composite score. Now, there's a bit of a solution here. So why not develop a regression model that predicts the concept of interest using the items on the test? So if we were to illustrate this with depression, we would have y hat subscore depression is a product of beta 1 of item 1 plus beta 2 of item 2 plus beta 3, etc., plus alpha. And I ask you to think about what does each B represent here, and what is A? I encourage you to think deeply about it, because I may or may not tell you. So, but the question is, what's wrong with this picture? What is missing? Spoilers, something is missing. Well, let's look at the path diagram that I've illustrated here. It should look very similar to the previous path diagram. However, instead of all of the items loading as 1, on our latent trait of depression, we have each of the beta weights. All right, so that's problem one. Problem two is, well, that tests that we use to measure a concept or construct typically have a moderate to large number of items as a product of, well, domain sampling theory, as well as our goal of increasing reliability. So with this whole situation comes a whole mess of relationships, those covariances, correlations, to show how all the items relate to each other. And alpha, if you can recall that far back, excuse me, sorry, I'm going to take off Archie's bell so that you can't hear it. So, yeah, so with this comes a whole mess of relationships across all the items. And alpha is just one method to try and summarize all those relationships by looking for a single consistent pattern. But alpha doesn't work so hot if you have multiple patterns. What if you have multiple components of your score? And what if some of the items are negatively related, so the term is reverse coded? Well, that's a problem. Now, to illustrate just the enormity of this data problem, I've included here a correlation matrix for a 24-item test. And what this illustrates is the correlation between every single item with every single other item. Across the diagonal is 1, because when you correlate something with itself, it's 1. You can look at either the bottom triangle or the upper triangle, they're symmetric. And each box indicates the correlation coefficient between the two test items of interest. And I encourage you to pause and zoom in and look at the correlation matrix, because what I want to point out is that these correlations are all over the place. Okay, so problem 2, let us continue. So alpha gives us a single value to summarize the relationship amongst our items. Now, it does this with very clear conditions. So it works if we have only one consistent pattern. That's the condition. So that one consistent pattern means we don't have multiple constructs, every item is in the same direction, and that everything is equally related to each other. It had some serious, strong assumptions built in, is what I'm trying to have you take away from this here. So if we could measure the concept directly, we could do this entire process differently and reduce the entire matrix on the previous page down to a single value as well. So a single correlation. It's a pretty neat concept. So next time, that's where we're going. In the interim, I'll see you in a bit. Bye!